Hi guys, this is lesson 2.7 on friction. So what we've done so far is set up net force equations, but we've been ignoring friction, which is in most of our net force equations. So in order to study other concepts, we've ignored this so far and assumed that things are frictionless, but this isn't really realistic because in order for something to move, there actually has to be some friction applying. If I'm standing on perfectly smooth ice, super slippery ice, and let's say I have like curling shoes on, but two of the really slippery curling shoes, I wouldn't be able to move forward because there's essentially no friction between my foot and the ice. And if there's no friction there, then there's no force to be pushing me forward. So friction is actually a force that causes a lot of the movement of us walking across the room or biking or doing any kind of movement. Couple definitions here. Static friction is the friction between two surfaces that are not moving, so hence the word static. And this keeps us from sliding on the ground when we're standing still. So if we're just standing still, there's friction between our feet and the ground that's keeping us from sliding across the room. Kinetic friction is the friction between moving surfaces. So the word kinetic is talking about movement. So this is the kind of friction that might slow a car down on the highway. This is the kind of friction that is always there between a car's tires and the highway, which is why even on a really cold day, there might not be lots of icy buildup on Highway 2 because the kinetic friction is able to keep the ice at bay. So in Physics 20, we consider two variables that affect the amount of friction that an object has. So the surfaces in contact. There's a very different force of friction if you're standing on ice than there is if you're standing on sand. These are two different surfaces that have different amounts of friction. The second thing is the amount of normal force between the surfaces. And if you recall from last week, normal force is essentially perpendicular to the surface. If we're on perfectly horizontal surfaces, it's the opposite of the force of gravity. So it's essentially mg, just in the positive direction instead of the negative direction. For COVID, we are skipping anything on angled surfaces, but you can expand this to be done on sloped surfaces, kind of like you see up here in the notes, but we've skipped quite a few of these lessons. Now, one note is that surface area does not affect the amount of friction that is on an object. So even if your shoes are bigger, it's not going to cause more friction between your shoes and the ice. Here's a diagram that shows the force of friction will balance the applied force. Now, this is happening when an object is not in motion. So if we have somebody standing still and there's an applied force pushing behind them, let's say you're on ice, for example, that person is going to remain standing still because the force of friction is counteracting the force applied until the force applied is big enough to counteract force friction and overtake it. So if it's big enough, then the person will start moving in the direction of the applied force. So static friction is keeping this box in place until it starts to move. Once something is moving, it's kinetic friction that's now at play. Here's the formula for force friction. It's equal to mu Fn. Fn being normal force and mu being a Greek letter that stands for the coefficient of friction. This is a unitless constant that we use, and this changes depending on the surface. So if you look at the next slide and make a note here, this is on page 183 of your textbook. We have these coefficients of friction figured out for several different materials. So for example, a rubber tire on dry concrete has a coefficient of static friction of 1 and a coefficient of kinetic friction of 0.7. So just for an example, here. So lots of times I'll give you questions and I'll tell you that we have maybe a steel item on dry steel, and how frictionless or how much friction would those items have when sitting against each other, static friction, or moving against each other, kinetic friction. The larger the frictional force, the larger the coefficient of friction. So something that's really slippery, like Teflon. Teflon is basically your non-stick cooking surfaces, like your frying pans. Those have really small coefficients of friction because they're really quite slippery. Something with a bigger coefficient of friction, like a rubber tire on dry asphalt, is going to be important because we don't want to slip around on dry asphalt when we're driving on it. So you can see why we pick some of these things for our everyday materials for cars, for instance, or cooking implements. All right, so let's go to the formula sheet for 1 second. I'll show you that we're in the dynamics section now. We've done the force net equals mass times acceleration, Newton's second law. We've done force of gravity or weight equaling to mg. Now we're on to the third equation. Force friction equals mu times Fn. So for this question, we're going to start with our formula. Okay, force friction equals mu Fn. You'll see on the previous page, when it's on the Physics 30 formula sheet, they put absolute value bars around the forces. That's because they're not concerned with the direction of the force in this equation. We're more concerned with figuring out what the force might be, what the mass is, what the coefficient of friction is. So essentially, these absolute value bars turn anything that would be negative positive. So in this example, Katie is pulling a wheelless suitcase across the floor. The suitcase has a mass of 7.6 kilograms. The coefficient of kinetic friction between the floor and the suitcase is 0.20. What is the force of friction? So we're trying to solve in this question force friction. That means that we must have information for mu, the coefficient of kinetic friction because the suitcase is moving, and Fn. Now Fn, remember, is the opposite of force gravity on horizontal surfaces, which this is. Now, what does that mean? Negative force gravity, if you look at your formula sheet, Fg is equal to mass times acceleration due to gravity. What is acceleration due to gravity? Well, it's that 9.81 number. So what's going to happen here is we have a negative 9.81. Two negatives are going to make a positive. You can jump right to this formula here, that force friction is mu m G. And you just need to understand that the absolute values have taken away any negative signs that would be there. So you're ready to sub in your numbers. For this one, our coefficient of kinetic friction was 0.20, and that is unitless. Our mass, 7.6 kilograms, and 9.81 meters per second squared. If you're worried that you're going to forget about the absolute value sign, making it positive, you can put a negative 9.81. You would just want to add a negative with your mass as well. So you'd want to make sure that you put a negative in front of your mass if you're going to put a negative 9.81. They'll cancel out and give you the same answer either way. So multiply these together. We're doing 2 sig digs here, and we get 15 newtons for the force of friction. If I wanted to have a free body diagram to go along with this, I could draw my 7.6 kilogram suitcase. I can draw my normal force and my force gravity. We've also got an applied force pulling the suitcase, and what we just found being the force friction that's working against the applied force. That would be a complete free body diagram. All right, a 750 kilogram car is now traveling 30 meters per second on dry asphalt when it skids to a stop. This looks a lot like a kinematics equation, but if you look at what we have initial velocity, we have final velocity being stopped, and we have mass. There isn't a single kinematics equation that takes into account mass, so we really don't have enough information to go to a kinematics equation. We have to start with dynamics or Newton's laws first in order to find acceleration, because Newton's second law says F equals ma. So if we have information, we should be able to find the acceleration of the car. So what kind of information might we be able to find here? Well, let's start with a free body diagram. We have a 750 kilogram car. Normal force and force of gravity will be canceling out because the car is not moving vertically. And then this car is skidding to a stop. So the only force at play here is a force friction. You're no longer applying a force to the car, you're just skidding along the road. So we've got our net force only being accomplished by a force of friction. That's it. So if I sub into this, what do I know about force friction? I know that this is mu mg. And what is F net from your formula sheet and from Newton's second law? ma. Now we're trying to find acceleration so we can use a kinematics equation. I'm going to divide both sides by m and cancel, so that acceleration is equal to mu g. Ends up being pretty simple. We have to figure out from our textbook what is the coefficient of friction on dry asphalt, and this is a car, so rubber tires on dry asphalt, when it's skidding to a stop. So this car is obviously moving. You need to find the coefficient of kinetic friction of rubber tires on dry asphalt. Pause the video and I'll meet you back here. So I'm getting a coefficient of friction from the chart to be 0.8, rubber tires on dry asphalt, kinetic friction, and 9.81 again for acceleration due to gravity. Multiply those together, and I'm getting 7.8 meters per second squared. Now, we have absolute value bars in the equation, so we didn't have a negative on the 9.81, but we need to think logically at this point and decide if acceleration is positive or negative. When you're using the force friction formula, you'll always get a positive because of those absolute value bars, but if you have something like this where the car is slowing down, then the acceleration certainly has to be a negative number, and you'll just have to put that in. All right, that was part one. And now we have enough information to go back to the kinematics unit and find what the question's asking for. So how far did it take the car to stop? We're looking for a displacement. We have initial velocity. We have final velocity. And we now have an acceleration. So if I look at my formula sheet and I pick a formula there, there's lots to choose from. I'm going to choose this formula. and I'm going to solve for displacement. So I'll simply switch the acceleration and displacement in the formula, and I'll sub my numbers in. Remembering to use not just 7.8, but the number on your calculator screen, that's 7.848. So I'll go ahead and I will divide these numbers now. And I am getting 57 meters. So according to Newton's laws, we would have an acceleration of negative 7.8 meters per second squared because the force of friction is the only force in the horizontal direction acting on a skidding car. We would then use that acceleration in a kinematics formula to solve for the displacement that it takes the car to stop. Same question, but now the asphalt is going to be a rubber tire on wet asphalt. So if it was raining, how does that affect the ability for the same car traveling the same speed to come to a stop? So same initial free body diagram. Hopefully you've got a good idea of how to draw these now. So we've still got our 750 kilogram car that has a normal force and a force gravity canceling each other out, and we've got it skidding to a stop. So force friction is the only force acting on the car. So in my net, meaning all my forces equation, I put force friction only. Net force, according to Newton's second law, is mass times acceleration. Force friction is mu mg. The masses cancel out, so you actually didn't need to know the mass of the car here. And we'll solve for acceleration by subbing in the coefficient of kinetic friction for rubbers on wet asphalt and acceleration due to gravity. So a rubber tire on wet asphalt, kinetic friction is 0.5, and then 9.81 for gravity. And I'm going to have to put the negative on myself because it does disappear when we do the absolute value step in this equation. And I get negative 4.9 meters per second squared in this question. I'm now going to go ahead and I'm going to use that to find the displacement it will take this skidding car to stop. So I have negative 4.9 I can use. It's going the same initial velocity and it's still coming to a stop, final velocity 0. Same formula. Still using the entire number from my calculator, negative 4.905. And in this case, I'm getting it to be 92 meters. So this question will show us that even just a little bit of rain makes the stopping distance quite a bit more than it is in good weather. So this is another driving lesson that comes out of Physics 20, I guess. Now I'm going to reread the question because I don't think we're quite done. If the asphalt is wet, how much further will it take the car to stop? Well, initially, on dry asphalt, we calculated that it would take 57 meters. So here, how much further is 92 than 57? A simple subtraction there will tell you that it's actually going to take 35 more meters to stop. So that's the lesson for friction. There's not too many practice questions. It's more about reading the chapter and trying to understand what the reading is trying to tell you, trying to be able to speak the physics language. Okay. Page 190 has questions 4 to 6 on friction, and page 183 has your chart showing you coefficients of static and kinetic friction that you can use. Anything else on page 190, I think, has an angle to it, which we aren't doing. So that's it for this lesson. You just have to do 4, 5, and 6 from page 190 and reading of chapter 3.5.